5.1, an overview of the area problem. In this section, we're going to start looking at the area between two curves. For example, at some point we might be interested in finding this area for a lot of application type reasons. We're going to start off with some simple areas. So first, the area problem is defined as, given some function and an interval, the area between the graph of f and the interval a to b is determined by going straight up from a and b, the x-axis, and the curve. So I might ask you to find the area of f of x on a to b. That means find the area that's bound by the curve x equals a, x equals b, and the x-axis, or y equals 0. That's what it means to be the area. And you might remember from pre-calculus when we found area between two curves, or between one curve and the x-axis, sorry. We did that by finding rectangles. First we started with one rectangle, two rectangles, four rectangles, and eventually we ended up wanting to say we want a lot of rectangles. So we made an infinite number of rectangles using limits. We'll be doing that again a little bit in the next section. Today is going to be more conceptual. So we've got these three functions, and it tells us for each of these functions, we're going to find the area between the graph of f and the interval a to x, where a is -1. So in other words, I want to find the area of this rectangle in part A. Then it tells us, once we have that area, it says find the derivative of that area. And we're going to see some magic happen. So part A starts off pretty simple. Clearly we've got a rectangle. And we know the area of a rectangle is base times height. In this particular problem, we can see that the base, one end is x, one end is -1. To find the distance between those 2 points, we subtract them, x minus -1. That's where the x plus 1 comes from. The height of this rectangle is 2, it's a constant. Distribute that, we get 2x plus 2. It also asks us to find the derivative of that area function, which of course is 2. Hey, what a weird coincidence. I just noticed the derivative function, derivative of the area, is the same as the original function. What are the odds of that happening? Anyhow, let's move on to part B. Part B, we're looking at the graph of f of x equals x plus 1. We know the area of a triangle is base times height over 2. And we can see this is a triangle. Once again, our base is x plus 1 for the same reasons as part A. Our height varies. If we want to find the height of this triangle, we actually need to calculate f of x plus 1. Or we need to calculate f of x, sorry, which is x plus 1. Simplifying this, we end up getting x squared plus 2x plus 1 over 2. Or if I wanted to write that as 3 separate terms, I could say 1/2 x squared plus x plus 1/2. Don't forget the directions also tell us to find the derivative of the area, which is easy enough. Derivative of 1/2 x squared is x. Derivative of x is 1. Derivative of 1/2 is 0. Once again, that weird coincidence seems to have happened. The derivative of my area ended up being the same as the original curve. So odd. Let's look at part C, one more example. Part C, we've got the curve y equals 2x plus 3. And looking at the picture, between -1 and some value of x, we don't have a rectangle. We don't have a triangle. We have a trapezoid. And hopefully you remember the formula for area of a trapezoid. If you don't, here it is. B1 plus B2 times h, all divided by 2. B does not mean the base. It's not that x plus 1. The two bases of a trapezoid are the two parallel sides. If we want those parallel sides, we need to first plug in -1 to our original function. And doing that, y equals 2x plus 3, we end up with 1. Then we need to plug x into our original function, so we get 2x plus 3. So there's our base 1 plus base 2. The height of a trapezoid is the distance between those parallel lines. In this case, just like it has been the whole time, x plus 1, all over 2. As you can imagine, we're going to clean this up a little bit. 2x plus 4, x plus 1 over 2. Distribute. We end up with 2x squared plus 6x plus 4 over 2. Simplify that. We get x squared plus 3x plus 2. And just like in parts A and B, we're asked to find the derivative of that area function. And we're probably not too surprised at this point to see that it is 2x plus 3. I say not surprised because, once again, the area function turns out to be the same as the derivative of the area turns out to be the same as the original function. So this actually wasn't a coincidence. This is true always, which kind of gives us a shortcut to finding the area function. For instance, instead of drawing this picture and working all this stuff out, if I could think of something whose derivative is 2x plus 3, then I will automatically have my area function. So for instance, if I'm looking at the curve, organic part D, y equals x plus 2, instead of actually drawing that picture and trying to come up with some formula for a shape, I could ask myself, what can I find the derivative of that will give me x as an answer? And through a little bit of thinking, you might come up with 1/2 x squared. Then you might think to yourself, what could my area, or what could my function originally say so that its derivative is 2? And the only possible answer is 2x, because the derivative of 2x is 2. The tricky part is that constant at the end, because the derivative of any constant is 0. So we have to be careful there. We'll talk more about that constant as we move forward. This is called an antiderivative. And we use antiderivatives to find the area under the curve of a graph. Exciting, I know. So example 2 tells us to use the antiderivative method to find the area under the graph of y equals x squared on the interval 0 to 1. First, we'd like to come up with some area function. As indicated in the previous slide, that really means we want to come up with some function whose derivative is x squared. That might take a little bit of time to think about And we will learn some techniques later in this chapter to make this really easy, just like we learned shortcuts for derivatives. But go ahead and pause the video and try to think of something whose derivative is x squared. If you came up with 1/3 x cubed, that's almost perfect. The reason I say almost perfect, yes, the derivative of this is x cubed, or x squared, but so is the derivative of this. So is the derivative of this, and this, and so on. So we really need to figure out what number to put there. So for now, we'll call it c. To figure out what that c should be, let's take the point that we know. If we want the area just between 0 and 0, we should all agree that the area of this curve from 0 to 0 is 0. So we'd say if x was 0, the area should be 0. So let's plug that into the equation and see what c has to be. Zero cubed is 0, times 1/3 is 0, so c has to equal 0. Now, c will not always equal 0, but in this particular case, c does equal 0. We'll spend a lot more time later in this chapter figuring out what c has to be in various functions. But for now, it looks like our area is just 1/3 x cubed plus 0, but we don't have to write plus 0. Now we can put any number in for x that we want. The problem tells us we want to go all the way to 1, so we're going to put in 1 for x. Area under this curve from 0 to 1 would be 1/3 times 1 cubed, which is 1/3. And we can kind of verify this with some geometry. Let's look back at that original shape. The original shape was almost like a triangle. If I find the area of that triangle, that answer should be too big, not hugely too big, but too big. And I can see that my base and height are both 1, so my area of that triangle is 1/2, which is a little bit bigger than 1/3. So I feel good about this answer. So what we just did here was we found a way to find an area under a curve without knowing a specific formula for that shape. It's not a triangle, it's not a trapezoid, it's not a rectangle. This is kind of powerful, and we're going to be using it for a lot of applications as we move forward, especially physics applications such as position, velocity, and acceleration. Right now, I'll go ahead and pause the video and attempt all of these problems. Come into class with some good questions. Have a great day.